Yes, thank you. Thanks a lot for inviting me. I've been having a great time. Also, thank you guys for coming today. It's like I know the last day is not so easy to listen to more talks. Right, I guess the point of this project, which I should say, this is all joint work with Yulan. It was kind of like, for me anyway, was to try to start from the first principle and decide what is the correct definition of a boundary. So there has been lots of different boundaries, and we have to, like, you know, think about different topologies and different ways of going forward. So I want to somehow start from the beginning and see, like, what is it that I want and what I'm trying to do, right? So kind of, you know, instead of just building on top of things, kind of rethink the whole thing with everything that we know, to see where things naturally go. So let me say, start with like X is a metric space. So what is the boundary of X? So heuristically, this is the space of directions, right? To infinity. So this is the ways that you can kind of go to infinity. So what is it that you would want from this? So what is my wish list of a boundary? Okay. So you're a geometric group theorist. Like, I'm kind of pretending a little bit, but okay. So this card is geometric group theorist, right? So your first example here is that the G is a group, right? And then the GDS is a word metric, is a metric space. So that's kind of the most favorite metric space that you have in mind. The problem with this object is that this is not a well-defined thing. Depends on the generating set, right? So this is well-defined up to quasi-isometry. So if I want to kind of define a boundary, which is kind of a well-defined for a group, but I want to say the boundary of this group is something or the other, like the first thing I want from my list, this is not kind of like, this is a very much geometric group theory point of view, right? Like, that's not everybody's first item in the list, but I want it to be quasi-isometry invariant. So I want to know that if P from X to X is a quasi-isometry, then I have some F from boundary of X to boundary of X, which is a homeomorphism. So I want the quasi-isometry. So that's kind of the first thing maybe I want. But besides that, I mean, like, you could just, of course, do that. You can say, well, there's only one way to go to infinity. There's a one-point compactification always exists, right? It's quasi-isometry, there's no problem. So you don't want to do something silly like that. So you want this to be large, like as large as possible. So you just want to, you know, identify directions if you really have to. Okay, so don't do it kind of otherwise. But then you don't want this to be a space of just points. It's a space, right? So you have to pick a correct topology in it, right? So hopefully a topology with a good topological properties. Okay, so let's say this is our starting point. Okay, so where do we go from here? Yeah, so you can start from like a simple example, and to me, a kind of a most illuminating example here. So example is not a Gromov hyperbolic space, but is more like R2. Right, so this is a good example to keep track of. What is the boundary of R2? What are the space of directions in R2? How many different ways can I go to infinity? Right. So, well, the visual boundary is a circle, but that's not really correct, right? I mean, if you're thinking about quasi-isometry invariant objects, you think about quasi-geodesics, and the quasi-geodesics can spiral. They can do all kinds of crazy stuff, right? So I'm not gonna like list in this, you know, talk like all this weird theorems like that, but basically any quasi-geodesic ray can be sent to any other quasi-geodesic ray. Rays could do crazy things in infinity. You could fix a huge ball, and in the complement of that sends, you know, I mean, so all kinds of things can happen. Like, really, there is no way to distinguish these two directions, right? So I would propose that, you know, any natural boundary, meaning that has those wish lists, the boundary of R2 has to be just one point. There is nothing better than that we can do, right? So, okay, so here intuitively we would say the boundary of R2 is just a point. Okay, this already has lots of consequences. Like if you admit this much to yourself, you know, so your path is a little bit narrowed down already. Okay, so let's do the other example, which comes up here quite frequently. So let's say this is a Z star Z2, the so-called tree of flats. Okay, very good. So you have a flat and you have a tree, you know, and then in each place you have more flats and more sticks coming out. I'll draw them like that. Okay, so something like that. Okay, so what's going on here? There are two ways to go to infinity. You can just stay in this flat, or you can go up eventually someplace. And then you can stay in a flat or go up to someplace. The flat parts, really, there is no way to tell where you're going, right? You can just say that you're going to infinity in the flat. So you can just pick the quasi-isometries of this object, that you pick these sticks and you move them around in however which here you want. Okay, so going along the flat direction really doesn't give you anything, right? So the only ways to go to infinity is that you say, I'm going to this flat and I'm going away in the flat, right? Or I'm exiting all the flats. So I have an itinerary of flats, and that's what I have to remember, right? So I would say the boundary here is like a visual boundary, quotient by, like, you know, identify, you know, the flats are equal to points, right? So this is really what you should do. Like intuitively, this is the correct boundary here. And this is equal to the Bowditch boundary, right? If you think of this as a relative hyperbolic group relative to the conjugates of this Z2, this is the Bowditch boundary. So, and this is kind of nice, so that, you know, there's a natural boundary already defined from the geometric group theory, which matches the intuitive picture that you have, that the Z2 parts I cannot tell apart, but the other direction I can kind of tell apart. So this has to be my boundary. Okay, so so that's very good. So maybe visual boundary quotient by flats is a good idea. But it's the no, you're adding 1 point for every flat. So it's the Bowditch boundary. Yeah. The ends of Basset tree is not compact. This is, yeah, so this is a little bit larger than that. Yeah.
Yeah. Able to find. Yeah, no, that's true. So that's kind of like, yeah, okay. So it's kind of being picky. You're right. I mean, I'm cheating. I'm saying that the word metrics give you quasi-isometries, and then I want to say quasi-isometries. Right? So maybe I'm asking a bit more than I did, right? But at the same time, I'm kind of trying to define a force boundary, right? So yeah, I mean, I don't want to really think about which quasi-isometries come from different genetic sets. Right. There is no quasi-isometry coming from different genetic set that does the spiral thing, right? But still, that's a quasi-isometry. Like, so if I look at, I want this to be defined on metric spaces at the end of the day, or just use the metric geometry of the group only. Right? So yeah, you're right. I mean, somehow it is a particular point of view, but that's the point of view I'm taking. Right? I want it to be quasi-isometry.
Yeah, maybe that's not the best thing always, you know. So, but let's go forward. Okay, so that's very good. So and then our everybody's favorite example, which is let's say G is a Gromov hyperbolic group, right? So what are the space of directions here? So you can't really think of visual boundary because the geodesics are not good, right? So your space may not even have geodesics, or if it does, like there could be geodesics that are fair traveling, right? So the point of the Gromov hyperbolic groups is that if I have a phi from x to x, which is a quasi-isometry, and gamma is a geodesic, then phi of gamma is just a quasi-geodesic, right? But it stays near a geodesic. Okay, so if I want to be quasi-isometry invariant, I have to say a quasi-geodesic that is near some other quasi-geodesic is the same direction, right? So okay, so being near is the same. So it's not just a space of directions, kind of identifying flats. You have to also maybe identify some other things, right, along the way. So okay, so if alpha is near beta, then alpha is the same as beta. Okay. Okay, okay, go on. So you can continue this list if I had more time and I would do it, right? You can say the Morse directions in general have this nearness, and then sublinear Morse directions, if they're sublinearly near each other, maybe that's also the same direction and so on, right? But let me just give you a definition which intuitively matches what we've been talking about. So when would I say two directions are the same? So if you do this for like a longer time, you kind of realize that if I have two different directions, I would say, let's say you want to go to a particular place, and that's a different place from this other place. What does that mean is different place? Which means if I'm going towards this, I'm eventually going away from this guy, right? So I would say this is a very good definition of being different directions, right? Going towards that doesn't get you closer to the other place. It's getting you farther away from the other place, right? So I would say that means if I go over here, there is no efficient way to end up over there, right? And if I can, in fact, find the efficient way to go from here to here, then these guys were not really different directions. Okay, so if I'm walking for a long time in two different directions, but they can end up in the same place while being a quasi-geodesic, then how are these directions different, right? And this kind of matches the R2 picture. So let's define a definition. So I would say, so this is a kind of a pre-orders on the space of quasi-geodesics. I would say alpha is, so let's say alpha and beta are quasi-geodesics. Sometimes I write this as Q geodesics, and then this Q is a pair of constant K and K, which is the multiplicative and additive error of the quasi-geodesics. Okay, so if I write it like that, then this Q is a number, is a pair of numbers. Okay. Okay, so let's say you have two quasi-geodesics, then I would say alpha is less than beta, right? If for every R, so if there exists a Q such that for every R, there is a gamma such that the gamma restricted to the ball of radius R is the same as alpha restricted to the ball of radius R. Gamma is eventually equal to beta, and gamma is a Q quasi-geodesic. Okay, so exactly this picture. I would say going alpha doesn't get you far away from beta, right? I can go along alpha as much as I want, R, and then I find a gamma, which is uniform quasi-geodesic, that takes me to beta. Right? If I can find a quasi-geodesic that is equal to alpha for as long as I want, and eventually equals to beta, I would say this two alpha is less than beta. So if this picture holds. Any question about the definition?
Also, well, if they have to be, if this gamma wants to eventually be equal to beta, right? I don't have to say it, right? So given alpha and beta, there exists a Q bigger than the Q of this. So I can go from alpha to beta uniformly, right? Forever. Okay, so this sounds like a reasonable definition. So we just run with it and see where it gets us. Okay. Yeah. Anyway, so that's kind of like the main thing I'm selling here. That this is a reasonable definition, right? These guys are not different directions. Yeah.
What is this order reflexive?
I'm sorry.
What is this order reflexive?
Oh yeah, these are very good questions. So we will get to it. So
yeah, the short answer is basically relative hyperbolic groups, and never else. Yeah. So yeah, so we'll get to it. Okay, so let's just like define some basic properties of this. So if alpha less than beta and beta less than gamma does imply that alpha less than gamma. Obviously, alpha is less than itself. So this is basically a pre-order, but I want it to be a partial order. So I want to identify the things that are the same either way. So I define alpha the same as beta if alpha less than beta and beta is less than alpha. Right. So I define the class of alpha to be all alpha prime that are the same as alpha, right? And I define this is the partial order now. So P of X would be the space of classes of alpha. Alpha is a quasi-geodesic. Okay, so, and I would declare this to be the space of my directions going to infinity. All right. So since you asked this question, let me give you an example where this is not symmetric. Right? I was going to do that later, but okay. So a good example to keep in mind is this parking lot example. Or a staircase or whatever you want, which is you look at R2, you subtract a disk from the middle, and then you take the universal cover, right? So this is visually you draw like that. So you're outside of R2, but if you go around, you'll go up. And if you go the other way, you go down. So what is the space of directions for this space? Well, let's see. Let's say this is your base point. It's always good to pick a base point. We always do that. So this is your base point. You can go forward in this direction. I call this alpha plus, the counterclockwise. Right? You can pick in this direction. I would call that alpha minus. And then there is this direction. So maybe I call this beta. This is the flat direction. Right? And I tell you, the claim is that these are the only 3 directions to go to infinity. This example and some variations of this are presented by Chris Cashin, which I which I love. So I mean, like, so this will come up all the time. Like, this is a key example. This embeds into all kinds of spaces. So why are they, like, what are the actual quasi-geodesics? Well, of course, you can go out in some spirally way. That's one thing you can do, but those can always be redirected to this beta, right? If you stay kind of bounded distance to these guys or sublinear distance to these guys, actually, there are Morse. If you are sublinear, you have to be bounded. So alpha plus, so let me just write this down. Alpha plus and minus are Morse. If you want to fill travel them, you have to actually uniformly boundedly fill travel them, right? Or you actually get stuck into the flat part. And if you're in the flat part, you're in the beta. But there is one weird thing about this, which is asymmetry. The alpha plus and alpha minus are less than beta, but not the other way around. Right? These guys are Morse, so there is no way to go along beta and then get back to alpha plus in a uniform way, right? So if you come here, you kind of go away. This is your geodesics. But the other way, that's not true. If you're going around alpha plus for a long time, you can always come along a log spiral, and then you eventually hit beta. Right? So it turns out that the alpha plus and minus are less than beta, but the beta is not less than alpha plus or minus, right? And these are the only classes. Yes. This is like basically saying that you have a chain of flats following a Morse direction, which happens all over the place. Like the Crookiner is the first example, right? So every time you have this issue of flats chasing a Morse, this guy embeds inside of it. Yeah, this is just a simplified picture that appears all over the place, right? So, like, in fact, this is the main obstruction to relative hyperbolicity, right? Like you have flats and the flats intersect. They don't have bounded coset penetration. So this is exactly that picture. Okay, so what is a good topology to put on this, right? Yeah.
Are the quantifiers in the definition? It's Q ahead of time?
No, that's the thing. Yeah, so given 2 things are the same direction, if there's a uniform Q that works forever, but the Q is not bounded because I want to deal with all quasi-geodesics.
Q doesn't have to be related to the
You do. Like so with direction thing, as you also asked, the Q depends on alpha and beta. So we say alpha is less than beta. If there exists a Q, it could depend on alpha and beta. So in particular, it depends on the quasi-isometry constants. So the redirecting constant will be much bigger, but has to be uniform for every R.
Yeah, so in your example, Q has to explode if you want to start with geodesic in direction of beta and you want to spiral.
You can't, no matter how huge you pick, eventually you will fail. So no, it has to, it cannot happen. So no matter what, for all R. For all R. So any Q will fail for some R. So you cannot do it, right? But to go from here to here, just like 3 is enough. Why don't you get back? Right? So I would say that if I'm going along alpha plus, am I going far away from beta? No, because I can always redirect to it. But if I'm going along beta, I'm definitely not going in the direction of alpha plus. So there's an issue of asymmetry here. So if I want to define a topology here, the topology should be, so I have 3 points, right?
So if you're going around here, that's the open set. These guys are like Morse, but there is no open set separating these from these guys. So this is your other open set, right? Everybody is infinitely close to beta, right? But alpha plus F1 are not close to each other, and you cannot go from beta to this guy. So this is the topology. This is not a Hausdorff topology, right? I cannot separate alpha and beta, and that's actually so this was kind of worrisome for me, but I decided it's a feature, right? It kind of tells you that this exact issue is going on, right? That you have flats chasing Morse happening, right? So it signals to you something interesting is going on in your space. Okay, so okay, very good. Okay, so we want to now topologize this PX. Sadly, if I want to do this in a setup of the generic metric spaces, there are lots of really horrible metric spaces. There are metric spaces that don't have quasi-geodesics connecting 2 points. You can have all kinds of dead ends that you go forward, you cannot continue. And you know, like there's no uniformity of any kind, right? So at the moment, we wrote down some assumptions, which I'm going to write down. Hopefully, it looks natural to you. They seem to be holding for all reasonable groups. It's hard for me to go through all groups. But anyway, so here they are. So to just proceed, we just add some assumptions. I would love to have counterexamples for these assumptions or proof that they hold in general, but they hold for relatively groups and for RAGs and for kind of like the basic things that I can think of, right? So let's write them down. So the assumption A0 is that first of all, the space is a quasi-geodesic space. So every 2 points X and Y, there exists a Q quasi-geodesic, maybe Q0, connecting them. So there's this Q0 is uniform. There's a uniform way of connecting the 2 points, right? And every X is on some Q0 quasi-geodesic array. Let me just say Q0, right? So means any point I pick, any point X, the point X lies on some ray. There's a way to go through X and continue on. The X is not a dead end, okay? So that's assumption A0. The assumption A1 is, you know, because I want to pick representative of these guys, if there are ways to go to infinity that are less and less quasi-geodesics, that's going to cause some troubles. So I want to say for every A in this PX, for every class that I pick, there exists a Q0 quasi-geodesic alpha inside of it. So every class has a quasi-geodesic of a uniform constant. Okay, and then A3 is that for every alpha, there exists an f of alpha. So alpha is the quasi-geodesic again. There exists a redirecting function such that if beta is some Q quasi-geodesic ray and beta is less than alpha, then beta, let me write it like that, is F alpha Q less than alpha. Okay, so if I pick a particular guy and I have somebody else redirects to it, the redirection constant is uniform function of Q, which could depend on alpha, but doesn't depend. So it's like basically this says there are no big holes in your space. Sometimes you have a geodesic and there are like big circles which are less and less efficient. And yeah, so that means the gamma that redirects beta to alpha has a quasi-geodesic constant of this number, right? So I'll write it in green. So there exists, so for every R, there exists F alpha Q ray gamma that is equal to beta at the beginning and is eventually equal to alpha. Right, so the same definition, but I want the redirecting constant to just depend on alpha only and not in beta. So I don't want like to have different ways of going to alpha, which are less and less efficient. So that kind of, again, means there is no big hole inside of a space. Okay.
Is large scale geodesic? It's not that exists in large scale geodesic. What do you mean? Like large scale geodesic method space is. Yeah, you could be a graph or something and have this weird shortcut. Yeah, you can just add like paths of length, whatever you want, connect to anything else you want. The ratios are getting worse and worse, right? You can always produce metric spaces, which are kind of like this picture alpha and beta, and then connect them in some way that going along here is worse and worse quasi-geodesic. And I can have infinitely many of these or something if I want to. Yeah, you can build up crazy metric spaces like that. Where everything you want to say fails. So general metric spaces are not very nice. Right? So hopefully the groups are nice and they have these properties, right? But the work is a bit on progress. So yeah, we don't know exactly, what class of groups have this or all of them, or we don't have good counterexamples. Anyway, they seem to be okay for relative hyperbolic groups and for RAGs, at least, right? If I don't want to overpromise anything. Okay, any questions? Do I dare to use the water? I do not. I don't want to open my mouth and say this. I don't know. No, I don't have any counterexample in mind. No, but I don't feel, I'm not a geometric group theorist. I don't have a good picture of all possible groups and what crazy things they can do in mind. Or if you present group, if you present the groups, you can definitely, exactly. Yeah, if you present a group, you can definitely, exactly. So that's what I'm trying to avoid, Yes, so now that I have the assumptions, I'm going to tell you topology. These are the minimum things that so I want to write the most natural topology, and this is what I need for a topology to be a topology, right? So, okay, so we define a topology using a neighborhood basis. So the neighborhood basis is things of like this kind, U alpha R. Alpha is a quasi-geodesic. R is a number. Alpha is a quasi-geodesic array. Yeah, there could be Q0. It doesn't have to, let's say Q0. Doesn't have to be. So what is this set? So I want this to be the set of points B in PX, right? That everybody in here can be redirected to alpha up to R. So basically, I want to say two directions. What is the neighborhood of one direction? Neighborhood of one direction is all the other directions that up to R, they haven't gone away yet. They can still go back, right? So up to R. So I would say for every beta in B, which is a quasi-geodesic ray, a beta can be F alpha Q redirected to alpha at radius R. Okay, so that's why I need this function. Otherwise, I have no way of writing down this sentence, right? So what does that mean? So this is my alpha, and I have a B. B is a cluster of different quasi-geodesics, right? There could be a whole bunch of them.
And any one of them that I pick, if I look at it up to radius r, this can go in here. So in particular, the fact that I have this condition 2 means the class of alpha. So note that A2 implies that the class of alpha is in the neighborhood of alpha, right? Because everybody who is in the class of alpha, by definition, can be redirected to alpha up to any number, right? So that's why. Okay, so no, it turns out it doesn't, right? So if you change the F alphas to bigger F alphas, the map is a quasi-isometry. So yeah, exactly. That's not a big issue. It's not sensitive to that. Yeah, you have to. There are things to prove here, right? This is very nice. Oh, no, it's defined for the class of alpha. It's fine. I mean, basically what I'll do is for every class, I pick this Q0 representative to not be too crazy. And then I define, this case. But if you pick a different class, you can redirect from the first guy to the second Y anyway. So then the neighborhoods that they define is basically the same and they're inside of each other, right? So it's a little bit flexible, but yeah, no, most definitely for the class of alpha, you can do that, yeah. Right? So again, so my hope is that I haven't cheated anywhere, right? What do I mean? Like I picked things that are the same, which they should really be the same, right? And I'm defining the cone topology. I'm saying that two things are close to each other if you cannot tell them apart up to some large distance, which direction you're going. If you're going from here and you can come back here, so then you haven't really gone far away.
At some point from X itself to this.
Yes, in fact you can. So you if you wanted to, you could define this. Yes, so let's do that. So you could think of a point X. So I want to identify this with a class of quasi-geodesic, right? So I want to say, look at so I represent again with X, the class of all quasi, so these arrays, such that the alpha of T is equal to X or some T, right? Then these guys are kind of indistinguishable from the other one. So I could then define my U alpha R to be exactly that. So I just pick a classes. So I could just pick this be in a PX union X such that the same exact thing holds. And then this will define topology on the union. Right? So it basically means every quasi-geodesic that goes to X can be redirected to this direction. That means X is close to this redirection, right? So it's exactly the cone topology. Right. So like basically points are also classes of quasi-geodesics. Points at infinity are classes of quasi-geodesics. So we go forward. So there are several theorems here. So first of all, this U alpha R do define a topology. You have to check a few things here. Like these are not open sets, they're open neighborhoods, right? So you have to say that if I pick this point A and I pick this neighborhood U alpha R, then there's a smaller neighborhood that for every point here, there's a neighborhood which is stays in another neighborhood. This kind of like extensions of this transitivity sentence kind of prove that. So they do define a topology. So I call this so PX with this topology is what I call the boundary. Okay. So the same way you can do it for X union boundary X. So there's a topology in here. So this is a Bowditchification. Every point, meaning that every point is in here is a limit of points over here. Is invariant
under quasi-isometry, right? So this should be relatively clear, right? I mean, our point here was to write down a definition so that this sentence doesn't require proof, right? So, and it's kind of like that, like, because everything is quasi-geodesics, everything depends on everything. So the only thing really you have to check is this question of like, if I make the F's bigger, would that make a difference? And it doesn't. So at the moment you check that, so that doesn't, because if I pick a bigger F, I can find like a bigger R to this neighborhoods nested inside of each other. So that's the only thing you have to check, which is some kind of geometry argument. And then you have that. Okay, so that's right. That's correct. Oh, embedding. No, sadly, I see, but no, you get a quotient. That's not good. So yeah, maybe answer that. The problem is if I pick the product like Z cross Z, for example, Z has two boundaries, but then becomes R2, so then they die out. That's right. That's right. Defines the map, but it's not homeomorphism. Yeah, that's right. But it's continuous. That's right. That's correct. That's right. That's correct. Yeah.
Topology on X.
I had a metric on X. Yeah, that's right. But just about, yeah, that's it. It's the same.
That's correct.
So I guess I should say here that you have this kind of basis neighborhood, and also you have a usual URX together, right? And this defines the topology on the. That's.
So you restrict to only the Morse rays?
Yeah, that was a perfect. I'm kind of remembering. If you restrict this to Morse rays, you will get the Morse boundary in the detection mechanical topology. And if you replace the sublinearly-Morse rays, then you get the sublinear-Morse boundary.
Right. So there'll be a talk about the sublinear-Morse boundary. So I'm not going to get too much into it. Yulan is going to give a talk on this. But these kappa boundaries, they're all subsets of this boundary. They're topological subspaces. Okay, and then you can try to like understand what this is. Yeah.
Compact.
Very good. So right. So the downside of this is where is it compact and where is it Hausdorff, right? For metric spaces, you can always produce metric spaces, but this is not compact.
Again, for groups, so there is no proof of compactness because it fails for geometric spaces. But for groups, it's possible. so I don't know, right? So at the moment, I don't have a counterexample, but that's not because I've thought about it for a long time, right? So I just checked some basic examples. It seems to be compact, but maybe I'll tell you what I can actually prove, right? And then the number of open questions is quite large. So this is in infancy. So a special case, or let me say key example or motivating example. There's a notion of metric spaces looking like relative hyperbolic groups. These are called the asymptotically tree-graded spaces. They're introduced by Sapir and Drutu. So I would say X is asymptotically tree-graded with respect to a family of subsurfaces N, right? Maybe I won't write this down so much since I really don't have any time at all. It basically means if you take the asymptotic cone of this, all the triangles will be near the limits of this N. So except for these N's, it's like a tree, right? It's exactly what you expect from triangle, the relative hyperbolic groups. So the other way of you can saying it is like every time you have a fat polygon, the fat polygons turns out to be near one of these ends, right? And okay, so and these ends are not near each other. So in the asymptotic cone, the intersecting number is exactly 1 point. Or here they have a bounded set that are near each other. Okay, so of course it's possible that this N has itself a non-trivial geometry. Maybe you're killing off too much. So let's say you're not doing that. So I would say X is ATT, yeah, right? If it's asymptotically tree graded, but if the boundary of this ends is trivial. So let's say the ends are flat themselves or something like that, right? So this is kind of the first case to consider. So this is the only one we consider carefully. And in this case, the theorem again is that if X is ATT, then boundary of X is compact and metrizable. Right? So these are the good guys. That everything looks very nice. So I mean, yeah, in fact, so if X is the relative hyperbolic, right? So if X is the Cayley graph of a relatively hyperbolic groups where the boundary of H are point, then the boundary of X is equal to the Bowditch boundary. Okay. So you get the correct answer at the places that you're supposed to get the correct answer. So what is the advantage of this over the other definition of Bowditch boundary is that you don't have to know the structure of the groups, right? The Bowditch, the relative hyperbolicity is not something that is canonical. It depends how do you pick H is and so on. I'm just using the metric geometry of X to define the Bowditch boundary at the minimum, right? So if the peripheral groups, they don't have any hyperbolicity inside of them, boundary being a point means you have no hyperbolicity, right? In that case, then you have a different definition of Bowditch boundary. It doesn't use the group at all. It's just a space of quasi-geodesics up to redirecting with this particular topology. Right, so I guess that's my cue, but I started late. Okay, so anyway, so the open questions are, when is this compact? So it would be nice to have counterexamples where this is not compact. It's compact for the Krokiner. I was going to spend some time going over the Krokiner, which is very interesting here in particular. So we can identify different directions in Krokiner. So in that case, it is compact, but not Hausdorff. In fact, one plausible conjecture or guess is that these are the only ones where the thing is Hausdorff. So it's never Hausdorff otherwise. Like you could potentially guess that the Hausdorffness is equivalent to being asymptotically tree graded, right? But I don't know for sure. Anyway, seems to be an interesting definition at least. It matches what it's supposed to match at the beginning of it, right? And brings at least some questions if nothing else. Okay, I'll stop here. Thank you very much.